Welcome. In this session, we'll work through the details of the Lagrange dual for a quadratic objective that has a set of linear equality constraints. What we want to do is this function, we have a symmetric positive definite matrix, so it's invertible, and this is the Lagrange function, which is the objective plus the multipliers times the properties. And we can find the partial derivative with respect to W of the Lagrange function as you do recall this, don't you? You do recall how to differentiate this? Is that the derivative of the Lagrange function with respect to W, that will be 2 times the term that precedes the vector argument, so that will be W transpose times the K matrix, and then that will disappear, and this will be mu transpose times M times W, so that will be plus mu transpose times M. So now what we do is we set to 0. So let's solve for, let's call it an interim. Let's say that there is some V that we're going to solve for. That is, instead of W, I'm going to use V, and this will clarify some things that will follow, because this will be the optimum for the dual, which is, and then we'll have to do some reconstruction to find it for the primal. So what we'll do is we'll set this equal to 0. So that would be we want V star, let's put a transpose times K plus mu transpose times M equals the 0, 1 form. So the first thing I'll do is I'll transpose that. So that would be equivalent to K transpose. Oh, but this is symmetric, so that's just going to be K later on. That'll be K times the optimal vector for this problem, and I'll take this over to the other side, and that equals, so I transpose that into M transpose mu, and I can now, oh, that'll be minus, and that is equivalent to saying that V star equals, this K transpose can be written as K, it's invertible, so I can say that's minus K inverse times the transpose of the constraint matrix times the Lagrange vector. And now let's abbreviate. So I'll abbreviate. I'll need this in a moment. We'll abbreviate a matrix B, which we'll define as M times K inverse times M transpose. And you can see partly where this K inverse M transpose is, and in a moment we'll see where that B will turn out to be useful. So now let's take a look at this. So the Lagrange dual function that has the multipliers as its argument, well, that is the argmin over all V in the objective vector space of the primal function. And that equals the Lagrange function, where now we take this solution, that V star, we insert that, and our multipliers are still unknown. So when we work this out, now this is a good moment for you to pause this and pull out some pencil and paper and actually do this derivation. So that equals minus, I calculate that as 1/2 of the Lagrange multipliers transposed times that B matrix times the Lagrange multipliers, plus I take that constraint vector out of the primal and I transpose that and I multiply that by the mu. And when you're doing the derivation, don't be surprised if you see a mu transpose C, and you have to recall from linear algebra that's the same as C transpose mu. So let's observe, let's make some observations here. Observe that this is concave, and the closed form solution is we now take the partial derivative of this dual with respect to the Lagrange multipliers, and we set that to be the 0,1 form, and that is, when we do all of that, we see that we can immediately negate it, and then we differentiate this, and we do just a little bit of vector manipulation, is the optimal Lagrange multipliers can be found to be B inverse times minus the constraint vector. And so now we're almost there, right? So now we now have the optimal Lagrange multipliers. And the equation for that interim V star still holds. So what we can then do is we can then do some substitution, and I'll let you do that substitution because it's worthwhile. The substitution gives us the optimal vector for the constrained optimization problem is minus the inverse of the original quadratic objective times, we now take those optimal Lagrange multipliers as a vector and we transpose it and we multiply it by m. So what we've done here is we found an interim solution to the dual. We then used that and we observed that for that dual we can then find, for this dual function which only depends on the Lagrange multipliers, there's a closed form solution. And then when we know the multipliers, we can go back and we can reconstruct the original vector in the original vector space that the objective function needs. Now let's summarize this session. What we did was we used an objective that's a quadratic function. We used linear equality constraints, but we could use other simple equality constraints. A major extension that we'll get to is how do we use inequality constraints. And in the next class, we'll work through some dual examples. So in summary, the primal formulation is a min followed by a maximization, and the dual is a max followed by a minimization. Here the minimization was done using linear algebra, and then the maximum, because it was quadratic, was also found using linear algebra. In this dual form, what we do is first we find the Lagrange multipliers, and then we deduce the vector minimizer from those Lagrange multipliers.